So I want to reinforce what you heard on the con video, starting with the Newton's first law of motion. So Newton's first law of motion says basically that an object, if it's at rest, will stay at rest unless it has some force to make it move, and an object that's in motion will stay in motion at that same speed unless it has some force to change its speed. Of course, if something changes its speed or velocity, we call that acceleration or deceleration. Deceleration in terms of acceleration is just negative acceleration. So 3, 2, 1. So I want to follow up with the con video that you just watched. So the Newton's first law, Newton has 3 laws of motion, and they're kind of like, oh, that makes sense. Everyday things that happen can be related back to Newton's laws. His first law says that an object that is, the object that's not moving will stay at rest or not moving unless there's some force to make it accelerate. Now we talked about acceleration. Acceleration is just a change in velocity. So if it goes from a velocity or speed of 0 to some sort of speed, then that's acceleration. So have a force to accelerate or make it go from rest to something else. So an example, for instance, something at rest, Stonehenge, okay? These stones, unless you apply a force, are not going to move. Another example of something at rest, for instance, it's the proverbial, we have coins on a piece of paper here. So one of the things you probably know is if I pull that piece of paper out quickly, those coins, what will happen to the coins? Those coins will want to stay where they are. So granted, there's commotion and a force to remove the piece of paper, but those coins aren't attached to the piece of paper, they're free floating. So if you do it fast enough, the coins will stay there. Something at rest will stay at rest unless a force acts upon it. So something in motion will continue at that same motion unless acted upon by an outside force. I don't have a picture, but my favorite thing, and this has been a few years ago, where somebody, and I think it happened to be a female, on board the space station, or maybe it was one of our space shuttles, actually was in outer space and threw a hammer. Didn't throw it, sorry, but this is my hammer. Oh my goodness, that's a terrible hammer. But in outer space, basically, the hammer went that way. Maybe it was a screwdriver, I'm not sure. But my point is, in outer space, when it left with a specific, let's say it went 15 meters per second. That seems pretty fast. Okay, maybe it didn't go that fast, but it went with a certain speed, and it's going to go that certain speed forever because, well, they're actually not in outer space. They're still gravitationally associated with the Earth. So, but assuming they're in outer space, it will go forever because there's no friction, there's no force of another body to slow it down. So I think that is so cool. So this idea of an object at rest want to stay at rest, or an object that's in motion wanting to stay in motion, is generally called inertia. So objects have inertia. So the symbol we use for inertia is the letter L, and inertia is the natural tendency for an object, just like Newton's first law says, for the object to stay there, or if the object is moving, to stay at that same velocity, not to accelerate, not to slow down, unless another force is acting upon it. That's inertia. This is a very common everyday thing that we experience. For instance, if you're in the bus, and in this case, the caption says, this is when the bus first starts moving. So you're here in your kind of reference, your spot on Earth. The bus starts to move, and you end up wanting to stay where you are, so it takes you a little while. Basically, your feet go with the bus. If you're pointing forward, your feet go with the bus, and your rest of your stuff has to kind of catch up. Okay, so there's that initial, basically, you're going from 0, the bus takes off, there's zero speed, and then you have to kind of catch up with the bus. Now, when the bus is moving at a constant velocity, guess what? Okay, you don't feel any force. Okay? So there's no force being applied to you. Now when the bus goes to stop, that's another thing, because basically you've been going at maybe 20 miles per hour and the bus suddenly stops and you lunge forward, okay, because you have inertia or momentum to want to go forward. You didn't get the memo. Okay, so you have to go from 20 miles per hour to 0 miles per hour. You have to decelerate. You have another force working on you as you accelerate, negatively accelerate. So that's Newton's first law. So this probably makes sense to you. Inertia associated with an object at rest, or inertia associated with an object that's moving, is a function both of how fast, if it's moving, how fast it's moving, and how massive it is. So I have an example here of two people. I think this could be me in a few years. I tell my kids, okay, where I'm being pushed by my kids. So here we have the young lady here who is pushing two individuals. We have the guy and the kid. So the young lady, when she gets the guy moving, okay, if the guy moves kind of a similar velocity as the girl who's also swinging, he's going to have more momentum or more inertia. He's more massive. Another thing, though, what do you think about the force she needs to apply to get that guy moving? Okay, she has to apply more force to get the guy moving, to go from 0 to some velocity. So mass actually then is a player with regard to the inertia an object has.